Hello, pre-calc. We're going to be looking at a new idea. It's definitely related to some of our previous stuff called the antiderivative. So say we have the functions capital F of x and we have lowercase f of x, and they're defined on the interval x. So an antiderivative kind of works like this, where if I took the derivative of my big function f, it would equal the f of x, or my second function. So antiderivatives are like the reverse operation to differentiation. So like if we looked at x squared, and if we wanted to find the derivative of x squared, we would say, all right, I'm going to move the 2 out front, 2x, and then 2 minus 1 is just 1, so I don't need to write that. The antiderivative is kind of like the opposite. So instead of going down, we're going to move up. So I would say, all right, in order for me to end up with x squared, if I took the derivative, if I'm going the other direction, what would I end up with? So let's say I have x to the third. I'm just going to write this as 1/3. And I was going to find the derivative of that. Again, I would move my exponent down, so I'd still have 1/3, and then it'd be multiplied by 3x squared. And then 1/3 times 3 is going to just cancel out, so I'm left with x squared. So the antiderivative of x squared is really x to the third over 3, or 1/3 x to the third. I'm going back in time. I'm like moving up a level, so that I can determine what would give me a derivative of x squared. What would give me a derivative of 2x? You're going backwards. And one important thing that we have to add when we do antiderivatives is we have to do plus c. And c stands for constant. And so again, the reason is, again, think about what happens when we have derivatives. X squared plus 5. When I take the derivative, this 5 cancels out. It goes away, right? So I have to state that there could be a constant there, because technically plus 5, or x to the third over 3 minus pi, whenever I take the derivative of this, my derivative is going to be x squared, because this is going to cancel out, or this is going to cancel out. So these could both be potential solutions, and there's actually an infinite amount of solutions. So that's why when we take antiderivatives, we got to add the constant back in. We have to add the constant. So really, again, we're talking about capital F of x plus c is like your generic form for an antiderivative. So let's do some examples. I'm going to find the antiderivative of this function. Now note that my x to the fourth is in the denominator, so like a little bit of side work. If I were to think about, okay, 1 over x to the third, my denominator is getting bigger, which means my answer is really getting smaller. So I could rewrite this as x to the negative third. Again, I'm still trying to figure out what's this derivative. So if I use my power rule, negative 3 minus 1, that actually gives me negative 3x to the negative 4. So if I wrote this as, hey, this is negative 3 over x to the fourth power, I'm very close to what I want. I'm very close to getting this. So the antiderivative of this function f of x is going to be, I just got to get rid of this negative 3 on top. So the antiderivative, again, capital F of x is going to be negative 1, but I'm going to divide by 3, because we can always check our work with these, which is nice. So if I try to take the derivative of this function, what's the derivative of this function? Again, rewriting it like this, I would say, okay, I'm going to start by this is a 1/3. I would say, all right, I'm going to move this number out front. So negative 3 x to the, again, negative 3 minus 1 divided by negative 3. So negative 3 divided by negative 3 cancels out. I'm just left with x to the negative 4, which is the same thing as this. So I know that I correctly found my antiderivative, again, by moving back a step. I'm going back because when I took the derivative of my antiderivative, I got what I was looking for. Let's do another example. Let's say that we have the function e to the 2x, and we want to find the antiderivative. So again, if I think about what my derivative is, what my derivative of this function is, again, e to the x is itself, and then we use the chain rule. So it's really going to equal 2e to the 2x. So if I think about the opposite of this, again, because I want the antiderivative, I want to end up with this. So if I want to end up with this, I got to go opposite. And so instead of multiplying by 2, I'm going to divide by 2. Again, we can check our work by differentiation. So I'm going to take what I think is the answer and find the derivative of this function. So let's see here. I'm going to rewrite this as just 1/2. So this is really 1/2 e to the 2x. So we're going to take our initial function, and then we're going to use the chain rule. 2e to the 2x. So my 2 divided by 2 cancels out, and I'm just left with e to the 2x, which is exactly what I wanted. Therefore, I correctly found the antiderivative. And of course, because it's the antiderivative, I need to add plus c on the end of my functions because, again, a constant could be there that has since dropped out.